Alright, we're going to do some pneumatics examples here, but before we do, we're going to go over the equations that are going to be involved in these problems. So, recall that pneumatics is about using compressed gas to do work. So, we're going to be talking a lot about the ideal gas law. There are three laws that come from this ideal gas law, and we're going to show you where they come from right now. So, you've probably seen this before, PV equals nRT, but as a refresher, P is for pressure, V is volume, N is the number of molecules, which we measure in moles, R is a gas constant, and T is the temperature. So when we talk about pneumatics, we're talking about a compressed gas. So just to give you a little example here, got a couple diagrams. Got a little piston in here with a container. We've got a gas enclosed, and there's two situations here. We've got the piston up high, and then it lowers down, compressing the gas a little bit more. So this is where we can use the ideal gas law. We can use the properties of the gas at either of these points to solve for an unknown value in there. So if we start with PV equals nRT, and we divide both sides by nRT, what we're left with is PV over nRT is equal to 1. What this tells us is that at any point, so either right here, before or after, PV over nRT is going to equal 1. Either position, any position that we can think of. So we can use this to say that PV over nRT at one point is going to be equal to PV over nRT at another point. This is key right here. This is what we're going to use to derive those three laws I was talking about. So let's take a look at those three. So the first one is Charles' law, and this deals with constant pressure. So if we've got a container, and maybe we're changing the volume or the temperature, but the pressure stays the same. Well, we can find out missing values here by starting with what we had before. The number of molecules in the container is not going to change. R is a constant, so it's not going to change. That means we can cancel those out on both sides. And we know it's a constant pressure, so we can cancel those out on both sides. The pressure is going to be the same at any point. So that leaves us with V1 over T1 equals V2 over T2. That is Charles' law. Simple as that. So now if we've got a container and we know the starting volume, we know the starting temperature, and I want to decrease the volume to a specific cubic inch value or something of that nature, I could determine the temperature that the gas would be at if I can keep that constant pressure. Next one is Gay-Lussac's law. And this one deals with constant volume. So just like we did before, we start with this equation. And again, N and R are constant, so we can cross those out. In this case, we're keeping the volume constant, so that crosses out. And we're left with Gay-Lussac's law, which is P1 over T1 is equal to P2 over T2. So it's the pressure and the temperature before, and the pressure and the temperature afterwards. Last one, same concept. We've only got one property left, and that's constant temperature. So Boyle's law looks very similar to the others, at least when we start. We cross out N and R, cross out the T's, and we are left with P1 times V1 is equal to P2 times V2. So here we are, these are our three laws, and these equations are what you're going to use to solve problems involving pneumatics. Okay, let's get into some examples here. I should also note that for some pneumatics problems you will also need the equation pressure is equal to force over area. That's very common in any of the fluid power examples that you'll see, so just always keep that one in mind. But for now, we're going to focus on those 3 laws that we just talked about. So in this first problem, you can see we've got 2 depictions, but they're the same container. One is at the beginning and one is at the end. So you can see we've compressed that gas in there a little bit. And based on these values that we have here, we can see that the volume has changed, but we don't know the ending volume. The temperature has changed, right? So the temperature's gone down from 85 degrees to 10 degrees Fahrenheit. So what we need here is an equation that's going to use V and T. Also note that the number of molecules in the container has not changed. This thing is sealed. We've changed the volume, or we've changed the temperature, which will result in changing the volume, but the number of molecules stays the same. So we're making those molecules closer and closer together by decreasing that volume. Okay. So we know which equation to use. Very simple here, straightforward. We're dealing with volume and temperature, so we have to use the equation that uses volume and temperature. But it's not quite as simple as plugging it in. It's very close. It is quite simple, but we can't use Fahrenheit. Well, why not, you say? Well, Fahrenheit, if you look at 0 degrees Fahrenheit, it's kind of arbitrary. It's not really a minimum like we really want when we're dealing with comparing values. So what we need is an absolute temperature. We need a 0 that can be referenced as an absolute minimum. So that's what we use the Rankine scale for. You may also have seen the Kelvin scale. Same idea, different system. And so the Rankine scale is equal to negative 460 degrees Fahrenheit at 0. So all we're doing is just adding 460 to our Fahrenheit, and that gives us the Rankine value. So to clarify that, because I got a little mixed up there, to find the Rankine degrees in Rankine, all you have to do is add 460 to your Fahrenheit scale. So we're going to do that. Before we get 545 degrees Rankine, after is 470. Now we can just plug in our numbers. So we get 100 cubic inches over 545 degrees Rankine is equal to the volume that we don't know yet over 470 degrees. Solving for our volume, we get 86.2 cubic inches. And that's as simple as many of the problems are. The trickiest part is remembering to convert your temperatures into absolute temperature. So make sure that you're using Rankine or Kelvin. Okay, we're going to try another problem now. Here, containers are a little different. We've got a constant volume. You can see that from the pictures. Right? We know the pressure and we know the temperature beforehand. We know the pressure afterwards, but we don't know the temperature yet. So, we need an equation with pressure and temperature. Go in and we grab that second law we talked about. But we need to use absolute temperature, don't forget. So, we find temperature for the first one in Rankine. Second one we don't know yet. So let's plug in our values. 10 psi. PSI is pounds per square inch. Over 500 Rankine equals 20 psi over T2. Solving for T2, you get 1000. Remember, this is in Rankine still. And then we can convert it to degrees Fahrenheit by subtracting that 460. So as you can see, the temperature went way up just by doubling the pressure. Last example for you. So now we've started with a smaller volume and we're increasing the volume, and we want to know what happens to the pressure. So we're dealing with pressure and volume. We know which equation we want to use. Plug in our values. No temperature here to convert, so that's easy. And we solve for P2. We get that the new pressure is 4 pounds per square inch. Now there's one last case that I want to show you here. And there's another kind of problem that you might see with pneumatics, and that deals with absolute pressure. So we talked about absolute temperature, and absolute pressures, similar concept, but a little bit different, so I'm going to explain that difference to you here. So the gauge pressure, that's when we're talking about measuring something, right? You have a gauge and it tells you the pressure, if you can read the pressure value from it. So the gauge pressure is the measured pressure in a container, okay, but it doesn't account for the atmospheric pressure surrounding the system. So we can't really use this in some of our calculations. You might be asked, here's the gauge pressure, what is the absolute pressure for this system? So in that case, we got to look at the absolute pressure, and this is a very simple calculation. We just take the gauge pressure, that's the pressure that was measured, and we add atmospheric pressure. Atmospheric pressure, for your purposes, will always be 14.7 psi. In some cases in the real world this may change. However, this is the standard pressure that we're going to use here. So all you have to do if you're asked to find absolute pressure is take the gauge pressure and add 14.7 psi. So here's a question here. If a gauge reads 120 psi, what is the absolute pressure? All we do is add 14.7 psi to get 134.7 psi, and that is our absolute pressure. Well, that's it for pneumatics. Make sure you check out the videos on hydraulics as well.